Okay, so I'm going to finish off 2.3, which is the product rule. And one thing I'm going to say is write down your product rule somewhere and always just keep it handy or whatever rule you're working on. And some of these I'm going to answer in Part C, and some of them I'm not. I do not care about the conceptual questions. I'm here to help you answer much needed real questions. Okay? So this first one, forget it. I don't care about the expansion or the coming up, deriving an equation that suits that specific need. But this one, I do. So look at this one. Determine a quadratic equation when we're given, oh boy, I hate when that happens, when we're given two specific points. So one thing that students have a trouble imagining is these are just numbers. And the x, and they say, well, so is the x. Well, no, the x represents on a Cartesian graph a point on the x-axis, and this f of x represents the y. It's very important to keep that in knowledge when you're looking at these things. The numbers here just affect the shape of that graph, but they're just numbers, and all numbers are imaginary. If you can use your imagination more in math instead of trying to study rigid rules and memorizing things and squeezing a square peg into a square hole over and over again, not only will you enjoy math more, but you'll understand it faster. So when I'm missing three variables, by the way, there's a super fast way of coming up with this. When I'm missing up three variables, I'm going to need three equations. That's what I'll always need. And that's all there is. Missing three variables, you're going to need three equations. So I'm going to start with this equation. And I'm going to fill in what I know. Well, I can use this equation twice because I have this point here that will fit in for y. And wherever I see x, I'm going to put a 2. And I have this equation here that'll fit in for y. So far, so good. I have two equations that'll fit in. Okay, and this, remember to use your new x over here. Minus 1 squared times minus 1b. Okay, let's just make this a little easier to write, but we're going to hang on to them. I've got 19. What's 2 squared? It's 4, so 4a. What's 2 times b? It's just 2b. I like to have my numbers first, my letters next, plus c. There, that's a much clearer equation. Now all I have to do is find out another equation for c to fit it in there. Well, let's clear this one up. I got minus 8. What's minus 1 squared? It's 1, so it's a. What's minus 1 times plus b? Minus b plus c. Beautiful. I can rearrange this equation. And by the way, keep one of these equations handy for later. And you'll see why. I can just rearrange this so I get c is equal to b minus a minus 8. How did I do that? C stays here, plus b goes over there, minus a goes there, minus 8 stays on the left side. And now up here, wherever I see c, instead of writing c, I can write this. All right, let's resolve that a bit. 4a, let's group our apples. Here's an apple, and here's an apple. What's 4a minus a? 3a. Here's an apple, and here's an apple. What's 2b plus 1b? 3b. Here's an apple, here's an orange, and here's an orange. And bring it over this 8 over here, and we get 27. Pretty clean. Now we have an equation with two missing variables, which means we only need one other equation. Well, they give it to you right here. Oh, I stole this by accident. It's a 2. And that's when they give it here. They have a horizontal tangent at this point. Well, horizontal tangent means the slope is 0. So that means that the derivative of this is going to be equal to 0. So let's take the derivative of that. The c, when I derive it, won't exist. The b will just become a b because the 1 over the x goes in front of the b and the x gets a 2 with the 0 and disappears. This 2 comes down and goes in front of the ax. And you might say, well, we're missing 3 things again. But you forget we have the x coordinate up there for when the tangent is equal to 0. So this is now my third equation. If I put the minus 1 in here, it multiplies the 2, and I get this. If I rearrange it, I get this. B is twice as much as A. Beautiful. I now have another equation, and where do I replace it? Wherever I see B, I replace it with 2A in a bracket, just like substitution. Now I can resolve this. 3 times 2A, 6A. 3A plus 6A, 9A. What is A equal to? When I divide the other side by 9, A is equal to 3. B is twice of A, so B is equal to 6. And over here, C is going to be equal to B minus A minus 8. Well, B was 6. A was 3 minus 8. So 6 minus 3 is 3. 3 minus 8 minus 5. So C is minus 5. Now I can go back and I can say this is the equation. Three, 6, minus 5. There's a much smarter, faster way to do this, but they clearly wanted us to use derivatives. We didn't have to use the product rule, so I'm surprised they wanted us to do it. But the secret is recognize what our function was. What was our function? It's a parabola, right? Know what you know about parabolas. This is a much faster way. Parabolas only have one vertex. The vertex is the only place the slope is flat. So the only way this could be where the tangent is flat would be the vertex, which means I can use my vertex equation instead, which is something, let's call it factor D. X minus, it's not minus, it's plus 1. That's the only one you have to make opposite, squared, minus 8. This is always the y value, and that is always the opposite x value. For the vertex, the only thing I got to figure out is this, and now I'm allowed to take any numbers, any coordinates that I know to solve for this. Well, what's 3 squared? It's 9, so I get 19 equals 9d, the missing variable, minus 8. So 9d is equal to 27. So d is equal to 3. So that means this at front is 3. Great. Now if I go back and just say y is equal to 3, x plus 1 squared minus 8, and I expand this middle part, and multiply by 3, I get 3x squared plus 6x plus 3 minus 8 minus 5, and voila, A, B, and C without ever having to use derivatives. Okay, let's go on to the next one. And you should get full marks for finding sneaky ways of solving things. At least if I was a math teacher and my student found a sneaky way to solve something, I'd do it. For what values of x are not differentiable? Oh, I hate these. So we're going to sketch a graph of this. To sketch a graph of this, I want you to imagine or use your knowledge of what that is. That's a parabola, right? And it's a parabola that has 0 as a coordinate here and minus 1 as the y coordinate there. If you have trouble seeing that, it's like that. And that means instead of starting here at origin, it starts down here at 0, comma, minus 1. It faces upwards. It's got a plus. So it goes up here like that. We just need to figure out when this is equal to 0, when it crosses the x-axis. And I'll show you why for a second. Well, that's when x squared is equal to 1. So that means at plus 1, comma 0, and minus 1, comma 0. It equals to that. Now I'm going to draw the rest of it in red. So this is the parabola. Now, what happens when I put absolute value around it? It means any y values that were negative, which is all here, now bounce up sharply, go up like that, and come down sharply. So this red graph is the graph of that. And the rule says it cannot be differentiated at this sharp point and this sharp point. It can at this rounded point, which is now 0, comma 1, but it cannot be at this sharp point. So for what values of x can it be differentiated? Minus 1 and plus 1. Find a formula for this and sketch the graph of the formula. Well, keep in mind that this is going to be the same right here as this part of it. Okay? So what's the there? It's 2x. For here, it's 2x, and for here, it's 2x. And for this part, it's minus 2x. So over here, it's 2x, and over here, it's 2x. So that means if I'm going to graph it, and keep in mind, so I'm going to just move this over, actually get rid of that. If I'm going to graph this, I'm going to do another one, and I'm going to realize that it can't be differentiated at this point, but I'm going to find the point for it. When it's minus 1, this becomes 2. So when it's minus 1, this becomes 2. So that means right here I'm going to put a hole. And now minus 2x, let's say I take minus 2 there, it becomes plus 4. So like there. So I'm going to draw a line like that. Great. Now, let's take a point where it becomes minus 1 again, but this time it's oh wait, it's minus 2 there. Yeah, not the minus. So on the left side, I'm taking everywhere where it's the normal 2x derivative. Okay? And that means at minus 1, it's minus 2. So it's down here, actually, sorry. And then the next point at minus 2, it would be minus 4. So minus goes from minus 2 to minus 4. So it's actually going down like that. Yeah, because it's 2x. It's actually going up. Okay, so we have this crazy graph here. Like this. And we're going to put a circle there because it's not differentiated. So that's sort of the graph of 2x. Not quite. Then when we cross this line, let's multiply it by minus 2x. So when x is minus 1, I get plus 2. So I'm going to put a circle there. Now I'm going to put a 0 in there. So it's going through 0. Then I'm going to put in 1 in there. And it's going through there. And I'm going to put a circle around it. So for the middle part, I have a negative downward graph like that. And then on the right part, when this crosses right here, I'm going to go back to the positive formula because once we get out of that zone, we're back to the normal parabola. And I'm going to say, okay, what's 2 times 1? It's 2. Circle. What's 2 times 2? It's 4. Like that. Boom. And this makes a lot of sense when you realize that if that absolute value hadn't turned this portion, upwards like this, that the formula for the parabola would be just a 2x line straight through, even though they don't quite match. It's just right here, all of a sudden, the derivative gets flipped opposite direction because it has this weird bounce back. And that makes sense too, because if this was an upside down parabola, this would be the vertex for that. So you can see that if you put this in the Desmos, what was it? It was x squared minus 1, and you do y is equal to absolute value of x squared minus 1. There's the graph I drew, and then you can make that f of x, and then you can make h of x equal to the derivative of f of x, and boom, there it will draw it. If we click on it, you'll see undefined right at those points. Undefined. Because it can't take a derivative there at the endpoints. But there you go. I'll show you what happens if I remove the absolute value. Makes sense now, doesn't it? I'll put the absolute value back. See what it does to the derivative? I'll take the absolute value. The more you play with this, the more you'll understand it. Okay. Show the line is tangent to this curve. This might take me a while. Maybe, maybe not. You're showing proof. So you must come up with a left side equals the right side situation. Often, anyway. So show that this line is tangent to the curve there. So first of all, let's figure out the slope of this line. Let's bring the y to this other side. And I get y is equal to 4x plus 11. There's the slope. So that means the derivative of this, which clearly is going to be a problem, is going to be equal to 4. And then I have to find the point where that happens and make sure the point's on that line. Okay? So let's first work on, notice the math book uses y over and over, and they shouldn't because we should be using function notation. Let's rewrite this in an exponent. So instead of x squared, it's actually 16 times x. So minus 1. And you might say, well, is this minus 1 going to play a role at all? Not really. Because, to the minus 2 rather. X to the minus 2 is what this is. Not really, because this is like saying 3x squared minus 4. When we take a derivative of that, that's not going to matter. So we will have to use, so let's just get rid of it and rewrite this so it's clear. This is the same thing as that part. What happens when I take a derivative of it? I have to do the chain rule. So I have to put the minus 2 in front. Oh, in front of the 16, because this minus 2 is only affecting the x. And I have to lower it to minus 3. But then I have to multiply by the content of that, which is just 1. So actually, yeah, we can just use the power rule. My bad. So there we get that. What's minus 2 times 16? Minus 32 over x to the 3. That's the rewrite of that. Now I have to show what value of x when this is going to be equal to 4. Well, I got to get x above the denominator, x cubed. So I have to multiply by x cubed. By the way, what kind of graph are we dealing with? It's a rational being divided by x squared, and if x is 0, it can't exist. So it's going to have a hypotenuse, or a vertical asymptote there. Other than that, this number keeps getting divided by bigger and bigger numbers. So it's going to stay positive after that. Except when it gets subtracted by 1. Whew, that's a confusing one to imagine. Okay, so I have to multiply both sides by x cubed. And then to get rid of this 4, I divide it by 4. So I get x cubed is equal to minus 32 divided by 4, which is minus 8. So what's the only possible value where x cubed can equal minus 8? X must be equal to minus 2. Great, one step closer. X must be equal to minus 2 if the tangent is going to equal 4. I got to plug this in now. If x is minus 2, I get 16 over 4 minus 1. 16 over 4 is 4 minus 1, 3. So that means when x is minus 2, y is 3. Now, my last step is I have to show, using the line formula, that if I substitute all this information in, plus b, if I substitute this information in, along with my m is equal to 4, then I'm going to come up with this b, i.e. I'm going to come up with the same line. So minus 2 goes in here, 4 goes in here, so I get 4 times minus 2, minus 8. Y, 3 goes over here, plus b. Isolate b, b is equal to 11. So I've just proven that if this is to match 4, it does indeed come up with this line formula up here. Ta-da!